Okay, so we're going to now predict molecular geometry, and we're going to use valence shell electron pair repulsion theory, right? The name is not important, but you heard this in Chem 1, so valence shell electron, or Chem 2, valence shell electron pair repulsion theory. And we're going to use that to predict molecular geometry. This is probably one of the most important topics that we'll have in all of Organic 1 and 2, okay? It's not going to be very long, but it's very foundational. All right, so we're going to predict the molecular geometry, and we're going to do that by counting the number of electron groups around a particular atom, around a central atom, okay? Now, we're going to call it, for the sake of this conversation, we're going to call it a steric number. And the steric number is the number of sigma bonds plus the number of lone pairs, or it's the number of electron groups, okay? So when methane when we're counting the electron groups around methane, then we're going to go, well, there's an electron group right there. It's really a bond, right? Here's another electron group. Here's another electron group, and here's another one, okay? So there's 4 electron groups, or 4 bonds, 4 sigma bonds around methane. And so its steric number is 4, okay? Let's practice this a little bit more, and then we'll apply how we're going to use a steric number. So in ammonia, we have a bond, another bond, and another bond, right? That's 3 sigma bonds, and we have a lone pair, okay? But that's really 4 electron groups, right? Because a lone pair is its own electron group, and so is a bond. So it's 4 pairs, or 4 electron groups, and we're going to call that steric number 4, okay? Same with water. With water, we're going to say, all right, so there's 2 bonds, there's an electron group, there's an electron group, there's an electron group, and there's an electron group, right? So its steric number is also 4. So what are we going to do with the steric number? Let's move on to the next slide. With the steric number, can you see this from where you're sitting? Is that too small? With the steric number, we're going to go, all right, if the steric number is 4, then its arrangement of electron pairs is tetrahedral. See, those are methane, it was 4, and it's tetrahedral. In ammonia, our steric number was 4, and so it's tetrahedral. In water, our steric number was 4, and it was tetrahedral, right? That's our electron geometry. Now, our molecular geometry is going to be a derivative of that, okay? So if all of the electron groups are bonds, then it's going to be the same. If there's no electron pairs, it's going to be tetrahedral. If one of the electron groups is not a bond, but rather an electron group, electron pair, right? Then we're going to name the shape of the molecule Trigonal Pyramidal. We got this in Chem 2, so perhaps this is familiar to you, right? And it's like a flattened pyramid, right? It's a flattened 3-sided pyramid. Okay? Now, and so we're naming the shape of the molecule for just those atoms, right? We're ignoring that when we're naming it. It's there, but we're not using it in its name. Okay? Now, for water, we're naming the shape of this based upon those 3 atoms there, right? And so we call it bent. All right? So a couple more examples, which we'll be doing in the homework. But the steric number of BF3, you need the Lewis dot structure in order to do this. Is it BF3? That's right. BF3. The full Lewis structure of that is this. Now, I did that really fast because I'm familiar with BF3. But there's no lone pair of electrons on here, right? And I know that because I know how to do the Lewis dot structures. That might be something you might want to go back and review. So if can you see my steric number for BF3 is 3, right? There are no lone pairs of electrons, and so, I'm sorry, there it is right there, 3. And so it's trigonal planar, okay? And since they're all atoms, then its molecular shape is also trigonal planar, okay? And BEH2 looks like this. And there is a lone pair of electrons on BEH2. So that steric number, can you see it's going to be 3, 2 sigma bonds, and a lone pair of electrons. So its steric number is 3. So we know that it's, oh no, I'm wrong. There isn't a lone pair of electrons on there. I'm looking back down here. It's not, it's just that. Right? So its steric number is actually only 2, right? And so therefore these guys are going to get as far away from each other as they possibly can. It's going to be linear. All right, so let's go do an example, and then we'll practice this more together later. So using VSEPR theory, predict the geometry of a hydronium ion. Okay, so first thing I'm going to do is I'm going to draw out the full Lewis structure for this. You can't do this without doing the structures, okay? Okay, that's the full Lewis structure. I think oftentimes people are going to put a plus charge on it because the plus charge is actually shared over the whole molecule, okay, over the whole ion. So if that is the Lewis dot structure, its steric number, marker's acting up here a little bit, its steric number is equal to 4, right? And so its electronic geometry is tetrahedral. Am I writing too fast? It's tetrahedral. But its molecular geometry, right, is going to be just defined by those 4 atoms right there. And that is going to be, looking back at the table on the previous page, we're going to see it is going to be Trigonal Pyramidal. I'm having trouble with my marker here. Trigonal Pyramidal. Okay? Let's go back here to this previous slide. Do you see it there? It was, our steric number was 3, and it had 3 bonds and 1 lone pair of electrons, and so its molecular geometry is trigonal pyramidal. All right, hope that's helpful. We'll do more practice problems when we're together.